So last class we said there were d parameters for the mean and d parameters for the variance, one for each component. And how many more are there? Let's see what you guys said. So first of all, did everybody get D? Yes, most people got D. Okay, good. Almost everybody got D for the second parameter. What else did people put? Okay, so for the variance of each component, it really is just D, because you have each component and you're just looking at the variance. So you have x1, x2, x3, xd, right? You can think of the vector x as some vector in R to the d. It has D components, and you want the variance of each one. How many more are there? Let's see what you guys said. There's some more. In addition, there are how many more? Okay, and we have a pretty even split here between d times d minus 1 and d times d minus 1 divided by 2. And I will reveal one of these two is the right answer. Is it d times d minus 1 or is it d times d minus 1 divided by 2? How many more parameters are there? I will let you guys revote. So there's a nice split, 6 to 7. Let's think about it. Why would it be this one? Why would it be that one? What are the things we're actually estimating? And I will throw it to a revote. Let's do that. That'll be fun. So let's revote. And I'll give you a minute to think. Feel free to chat with your neighbors about is there a divided by 2 in there or not? So it's got something to do with d times d minus 1. Okay, it's open again. Take 2 minutes and think. Feel free to chat with your neighbors about what are the number of parameters. Okay, 1 minute left. You have to put in your answers again, even if you don't want to change your answer. Okay, 10 seconds left. Put in your guesses on is it d times d minus 1 or is it d times d minus 1 divided by 2? And we'll see if there's a consensus. All right. Let's take a look at what people said. Okay, so first one, d means, d variances, and how many of these extra parameters? 11 people are now in d times d minus 1 divided by 2. So some people have moved out of d times d minus 1, and that is the correct answer. Okay, first one is d, second one is d, and the last one is d times d minus 1 divided by 2. Does someone want to tell me what are these d times d minus 1 divided by 2 parameters? What is this counting? So I think people, if you knew that you had to divide by 2, then you probably know what's going on here. What is d times d minus 1 divided by 2 counting? What did you say? The covariance. Yes. Okay, so there's d, there's more parameters. There's actually these covariances. Covariance. These are the missing parameters that we don't have on our list yet. We have the mean and the variance of each parameter, and we have covariance. And there's d times d minus 1 divided by 2 of these. What does a covariance look like? Well, a variance just has an x1, but a covariance has x1 comma x2, or the covariance of x1 comma x3, and so on. And why is it d times d minus 1 divided by 2? Why? First of all, why is there d and then multiplied by d minus 1? What does that mean? And why do you divide by 2?
Possible permutations.
Yes, okay, exactly. So it's the possible permutations. I think I would make it crystal clear because I often mix up permutations and combinations. Let's say possible pairs. So we have d things, and you got to pick 2 of them. That's the possible pairs. This is the number of possible pairs of d items. So if you have d chocolates in front of you, and someone says, please pick 2 chocolates to eat, how many ways can you pick 2 chocolates? D times d minus 1 divided by 2. You have d ways to pick the first chocolate, and then once you've chosen the first chocolate, you have d minus 1 ways to choose the second chocolate, except you've overcounted everything by a factor of 2 because you picked the coconut and then the cream, and picking the cream and then the coconut is the same pair of chocolates. So the factor of 2 is this overcounting by the order. We don't care about the order. So there's x1 with x2 all the way up to the covariance of x1 to xd, and then you have x2 with x3 all the way up to x2 with xd. You don't write the covariance of x2 with x1 because we already have that one, right? So you end up with this triangle. This is called a triangular number as well, and those are the covariants. You can put all of this information together into a big matrix. So you can put this together into a mean. So this is the mean vector, which is the mean of x1 all the way up to the mean of xd. Those are your d means, the mean vector. And then you have a covariance matrix. There are d parameters. I think I somehow slipped a d into the word covariance, but there is no d in covariance. Covariance matrix. What is in the covariance matrix? The ij entry. The ij entry of the covariance matrix is the covariance of xi with xj. So on the diagonals, you have the covariance of x1 with x1 and the covariance of x2 with x2. The covariance of something with itself is just the ordinary variance. So on the diagonals, you have the ordinary variance, and on the off diagonals, you have the covariance of x1, x2, and the covariance of x2, x1. Those are both the same. So the covariances go on the off diagonals. You end up with this big triangle of all the different covariances. So this triangle. This is a symmetric matrix. The bottom half and the top half look the same. So this is a symmetric matrix. Symmetric matrix. And so these are all the parameters. If you want to write it down this way, you could say there are d parameters over here and d squared almost parameters over here. It's not quite d squared because some of the parameters are copying each other. So it's on the order of d squared. It's a d by d matrix, but actually there are d for the diagonal. The diagonal are the variances. Variances on diagonal. And then you have plus d times d minus 1 divided by 2. These are the covariances on the, say, the super diagonal. On super diagonal. That means above the diagonal. Okay, so altogether, you could write it like that. You could also say we have, altogether there is d times d plus 1 divided by 2. So that if you add these together, it's d times d plus 1 divided by 2. Is it d times d plus 1 divided by 2? Now I'm skeptical. I think it is. d squared over 2, d squared over 2 minus d over 2 plus d, okay, which is the same as d squared over 2 plus d over 2, okay. So either way. So that is what's going on here. When you have a Gaussian, you need the mean, which is in d dimensions, and you need this covariance matrix, which is a d by d matrix, but has about d squared over 2 entries. There's these little combinatorial factors that mop it up. Okay, so you have all these parameters, and last class, we never played with the above diagonal parameters. We never played with the covariances. We only played with the mean and the variance in each direction. So we had our circle and we were smooshing it out in different directions. So that is what we were doing in Desmos. Let me go to Desmos now. We had this. So this is in 2 dimensions. This is d equals 2. And we had this thing. It's supposed to be a Gaussian, but it's cut off. So Desmos said, you're too tall. So just cut the top of the hat off. And you'll see it reappear as we change things. But we could change it in one direction. We could change it in the other direction. And we never played with the possibility that you would rotate it. And so there is this third parameter, which is in 2 dimensions. It's a 2 by 2 matrix. Let's draw what this looks like in 2 dimensions. So when d equals 2, you have a 2 by 2 matrix. You have the variance of x1, the variance of x2, and the covariance of x1, x2. That is appearing on the top and the bottom. And the covariance of x1 and x2 basically encodes the correlation between them. So I have a slider that is changing the correlation. This is C for correlation. And as you slide that, let's see what happens to the distribution. So it kind of changes shape. So it's still a circle, a kind of an elliptical pattern, but it changes its direction as you do this. You can look from the side as well, how it is changing. And if you make the correlation very, very close to 1, now you see everything lives on this sort of diagonal, right? x1 and x2 are very highly correlated. They live very close together. So if you really want to model a distribution, even if you assume it's Gaussian, which is already a big simplification, you still have a lot of parameters to find. In 2 dimensions, there are how many parameters? 5. There's 5 parameters because there's 2 means, and there are 3 numbers in the variance, right? The variance of each and the correlation between them. If you move to even higher ones, so like for example, for the housing data set you guys did, you had 81, you're going to have like 81 squared parameters to estimate, which is quite a lot. So if you just do this sort of thing of saying every individual thing is Gaussian, the more parameters you have, the bigger it gets quadratically, and that is bad. We want to be able to do very large things, and if it's quadratic, we can't quite do it. So what are we going to do instead? We are going to come up with a method to reduce the parameters, And like every good method, it is not quite 100% correct, right? So there's a very famous quote in statistics, which is, all models are wrong, some models are useful. This is a great example of that. We're going to come up with this method. This method is definitely wrong, but it is sometimes useful. And that method is called the naive Bayes method. Naive Bayes method. Okay. Before I tell you what the naive Bayes method, any questions or comments about the number of parameters so far? Okay. And the naive Bayes method, what it does is says, let's pretend all the parameters that were quite difficult, so the d means and the d variances, sure, those were pretty intuitive. But these extra ones, these covariances, these are annoying. So naive Bayes says, let's pretend you have the means and the variances. Let's just pretend all of the covariances are 0. So naive Bayes says, pretend this is 0. Pretend this is 0. And you might think, okay, this is like totally nuts. Like you had d squared parameters and you made almost all of them 0. And you just said, let's pretend it's 0? Why does that make any sense? And the sort of justification of why this kind of makes sense is that, so we're pretending covariance is 0. Pretend the covariance is 0. And when you pretend that the covariance is 0, that is pretending that the individual features are independent. So x, for example, x1 and x2 are, and I'll say independent with a star, independent, star, and star means within each class. Each class. So naive Bayes says we're never going to deal with the covariance. We're going to always pretend the covariance is 0, and that is pretending that the components are independent within each class. So if we were to go back to this picture, we would set the correlation to 0, and we always have sort of axis-aligned ellipses where there is some amount of spread in the x1 direction, there's some amount of spread in the x2 direction, but the x1 and the x2 directions never have any correlation at all. And this is pretending that they're independent, and this will hold for each individual class. So what I mean by that for classes, remember, we have multiple classes. So for example, we could have an F1. Oh, there's F1. So there's an orange class. And so within each class, if you are a green class, then your x1 and x2 are independent. If you're an orange class, your x1 and x2 are independent. In a real-life data set, you'll have a mixture of oranges and greens, and so the x1s and the x2s could be correlated because they're both dependent on what class you are. We'll see maybe a very visceral example of this where it's easier to understand what this correlation thing, or this conditionally independent thing means. But that is the idea. So we kind of treat each class individually as one Gaussian, or as the x1s and the x2s as being completely independent, and then we do all our modeling based on that. And this is a big assumption. This is why it's called naive. Naive means kind of simple and like too much to hope for. But in practice, this works quite well. So I'll show you an example in a minute. But this is the idea. So we're just going to pretend everything is independent. And when you pretend everything is independent, then everything is now linear in the number of parameters. So the amount of work you have to do scales linearly in the number of parameters d, the dimension d of the data. Okay, any questions or comments about that? We're going to do an example to try to understand this thing in a little more detail and see how it works. And then we're going to do the real life example of doing the Titanic data set with naive Bayes. Okay, let's do the example. And what is my favorite example? What is my favorite thing to do in the world? It is to flip coins. So we're back to the coin flip problem that we started with. And there's just one small change. So we have the type heads versus type tails coin problem. And before we said you pick a coin out of the bag, you flip it. If you see a head on the coin flip, then what is the probability? It is the type heads tails coin. It is only 1/3, right? And this was our first example of doing a Bayesian classification. And now, so that was before we had just an x1, right? So before we had x1 was equal to heads. And the question is, what was the probability y equals type heads tails given x1 equals heads? That was what we did before. This was before. And then today, we're doing the same thing, but we're doing the two-dimensional version. We're doing flipping the coin twice. So instead of just flipping the coin once, you pick one coin out of the bag and you flip it twice. So same coin flipped twice. And you got heads both times. And so we're asking, what is the probability that y equals type heads tails given x1 is heads and x2 is heads? Okay. So this is the question. Last class, the answer was 1/3, or several classes ago. And this class, you have to figure out what it is. What is it now? What is the probability it's the type heads tails coin? And this is an example of why is this a naive Bayes thing? Are the coin flips x1 and x2 independent? Just as variables, x1 and x2 are not independent because they are both related to what type of coin you have. So x1 is not independent of x2. x1 is not, as a variable, independent of x2. But it is conditionally independent given the type of coin. So x1 and x2, let's put it in pink. x1 and x2 are conditionally independent given the coin. So if you know what type of coin you are, if you know it's a type heads tails coin, then x1 and x2 are independent. They're both two fair flips of some type of coin. If it's a type heads coin, they're both independent. x1 and x2 are coin flips from the same type of coin. So the thing that connects them, the thing that makes them not independent, is sort of this confounding factor of what type of coin you have, right? If x1 is heads, it makes x2 more likely to be heads because it's more likely you have the heads coin. But if you know what type of coin it is, then they are independent. And this is exactly the idea. This is the naive Bayes idea. Naive Bayes is this idea. So if you want to know the probability that x1 is heads and x2 is heads for each type, so given y equals type heads tails, this is the product of the individual probabilities. So let's say, let's write it like this. It's the probability that x1 equals heads given y equals type heads tails times the probability that x2 equals heads given y equals type heads, tails. So if you know the type of the coin, then you really can just multiply the probabilities. And these probabilities are very simple. If it's a heads, tails coin, what is the probability that any individual flip comes up heads? This is something you should know. So I will let you guys use this kind of formula, this conditional independence. X1 and X2 for each class are independent. And so if you just go through the same kind of Bayesian calculation we did before, you should arrive at this probability. And it's your choice if you want to do it with Bayes' theorem or you can do the picture proof. Either way, you can do it. So I'll let you guys think for a few minutes and try to figure out what is the probability. Any questions or comments before I set you free? Okay, I'll set you free for a few minutes. Feel free to chat with your neighbors for this one and try to really work out what the calculation is and see if you can get the actual answer. Okay, who needs more time? Who needs more time? A few people. Let me give another couple minutes. I think this is a good exercise to try because it really is like the fundamental of what it's doing, right? Like if you every time you run a Bayesian thing, like you are doing this, maybe you're making the computer do it for you, but you should understand what the computer is doing. So I think it's a really good one to try. And if you're stuck, it shows that there's something to learn. Okay, I'll give you another 2 minutes. Okay, 20 seconds left. Think about putting some kind of guess. Is your number going to be more or less than 1/3? Think about that. Okay, so time's up. Put in some kind of guess, and we will see what people said. Let's take a look. So you flip it twice, it's heads both times. What is the probability? It's the type heads tails coin. So it's definitely not 1. It's not, it could, because it could be the type heads heads coin, right? Like if you have the type heads head coin and it comes up, you flip it twice, you're definitely going to get heads twice. 0.5, 0.2, 0.125, 0.11, 0.25 is a good guess. 0.33, 0.33. So 0.33 is 1/3. That is what we got if we flipped it once. So let's think. So first of all, are we looking for a number that's going to be bigger or smaller than 1/3? Does someone want to say? There's like you should be able to argue intuitively. Is it going to be bigger or smaller than 1/3? Smaller. Okay. Can someone explain why it's smaller?
We've already seen heads twice, so it
Yeah.
increases the probability that the coin is head tails.
Right. So the sort of the more heads you see, the more evidence you have that it's actually the type heads coin, right? The type heads coin pumps out heads like all day long. So if you see a long string of heads, like if you flipped it 100 times and it was all heads, you go, well, is it the heads tails coin and we got super lucky, or is it just the heads coin and it's a typical thing that happens every day? So with 2 flips, the probability should go down. So you definitely want to guess something less than 1/3. 0.5 is definitely wrong. 1 is definitely wrong. 0.33 is also definitely wrong. Like it definitely needs to go down. So 0.25 is a reasonable guess. 0.2 is a reasonable guess. 0.125, these are all reasonable guesses. 0.11, 0.1. What you really should do is, if you are stuck on doing it with the formulas, just write down all the possible things that can happen. There's not that many things that can happen. How many things can happen? Well, we reach into the bag, and there's 2 choices, right? Which coin did we get? Then we flip the coin. That coin has a side A and a side B, 2 more choices. So we went from 2 things to 4 things, and then we flip it again. That's another 2 things. So there's 8 possibilities total. So write down the 8 possibilities. Count how many of them is it the heads coin? Count how many of them is it the heads tails coin, and give me the ratio. That's what you got to do. So let me reopen it for voting, because clearly there's no consensus here. I'm going to reopen it, and I recommend to you, I'll do it with the formulas, but you should try to do it. At least do it with the counting first, so you can see what it is. That's why I made it simple coins instead of some PQ probability thing, so that you could do it with counting. Okay, so let's do it again, and try to do the counting this time. All right. And again, feel free to discuss if it would help you to see what your neighbors are doing, if you need a hint. All right, 50 seconds left. Start thinking about what you're going to type in. I guess if you really don't know, put in 1, 2, 3. So I know how many people really have no idea. All right, 10 seconds. All right, let's take a look. What did people say? 0.125 is popular. 0.25 is popular. 2 people still strong in 0.2. The 2 people who stuck in 0.2 are right. It is 0.2. It's 1 out of 5. 1 out of 5. So let's see, how would you get 1 out of 5? Let's do the calculation. So one way to do it, and this is the sort of easy way to do it with this problem, because there's not that many things, is let's draw that little tree like we did before. So this is the sort of simple way. And this is the whole point of why I did a problem with heads and tails instead of saying, the probability is 0.7 and 0.3, is that you just count the number of ways. Everything is equally likely here. So first choice is which coin? Which coin? That is the first choice. And that splits, we reach into the bag, we pull out a coin, that splits the universe into 2. There's the universe where we got the heads tails coin and the universe where we got the heads heads coin. So this is the y value. Y is type heads heads, and over here is y is type heads tails, right? And this is how you should always think about these Bayesian classifiers, is for every given data point, you think of there's a universe where it's class 1, there's a universe where it's class 2, and given that it's class 1 or class 2, if you know the distribution, then you can fill in the rest of the tree. So this first step is always how every single thing starts. Okay, so heads heads and heads tails. Then we're going to flip it once. So the first flip, this is the first flip. First flip is this column, or this row. So this is the type, coin type is always the first thing, is the class. And then once you know the class, then you have the first and the second flip. Okay, in the first flip, there's side A and side B. For the heads heads coin, it's very boring. Side A and side B are both heads. So if it comes up heads, or it can come up heads, right? We have to write them down because there's 2 universes, right? Okay. The other coin is more interesting because there's one universe where it is heads and another universe where it is tails. So this is exactly what we had when we did the problem before, and this is why the probability was 1/3. There are 3 universes where heads came up, right? We said cross off this universe. This tails definitely did not happen given one coin flip is heads. There's 3 possible universes. In one universe, you're the type heads tails coin, and in 2 of those universes, you are the heads heads coin. So that was why we had 1/3 before. Let's look at the rest of the problem today. Heads splits again. We flip the second coin. Again, the universe is split into 2, depending on the outcome of the second coin flip, right? And for the second coin flip, what are the 2 possibilities here? Well, it's still the type heads heads coin. So again, this is quite boring. This is heads, 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 heads. For the type heads tails coin, it's more interesting because it could be heads or it could be tails. So it could be heads or tails. It could be tails or heads. Let me write it in the same order. Heads, tails. Okay. And so you can sort of aggregate. That is our tree of possibilities. And we can aggregate what is going on. So summary. Let's do a little summary. The summary is, this is the type heads heads coin, and it came up heads and heads. This is the type heads heads coin, and it came up heads and heads. This is the type heads heads coin, and it came up heads and heads. Type heads heads. Type heads heads. Very boring, the first 4 things, right? So in the first 4 universes, you pick the type heads heads coin, and you got heads heads. The reason it's on there 4 times is because actually those heads are at side A, side B. There are many different ways it could come up, but it always comes up with 2 heads. All right. For the heads tails coin, it's different. So for the heads tails coin, in this one it came up heads heads. But in this one, it came up heads and then tails, right? So I'm reading down the tree. Heads, tails, then tails. So it came up heads, then tails. heads, tails. In the next possibility here, it came up tails. So tails, then heads. Maybe I'll highlight it. Type heads, tails, tails, then heads. Right? So tails, then heads. And last but not least, it could have come up tails, tails. Okay. So we did 3 things, right? Chose a coin, flipped a coin, flipped a coin. So there's 8 total universes. Which universe are we in? Well, we saw heads, heads come up, right? We saw heads, heads come up. So we don't see the first thing. This is always how classification goes. You don't see the class. You just see the x values. So this is the y value. These are the x values. You don't see the x values. You only see the y value. And based on the y value, you get some information, based on the x value, you get some information on which y is more likely. In this particular case, we can completely eliminate some possibilities. And the possibilities we are eliminating are these 3. These cannot happen. Let's do it like this. These cannot happen. Cannot happen. And that is because x contains a tails. And we were told, we observed 2 heads. So the only things that are consistent with our observations are these lines where we got heads, heads. And of these universes, how many of them are type heads, heads, and how many of them are type heads, tails? There are 4 heads, type heads, heads. And there is 1 universe with a type heads, tails. And so what is the probability of the coin being type heads, tails? It is 1 out of 5. There's 1 universe where it is type heads, tails. There are 4 universes where it's type heads, heads. So the probability it is type heads, tails, given x1 is heads and x2 is heads, is 1/5, and it's really 1 out of 4 plus 1, right? There's 1 universe where it's type heads, tails, that's consistent with heads, heads, and there are 4 universes where it's type heads, heads. Okay, so 1/5, also known as 0.2. All right, so this is the picture proof that is going on here. Any questions or comments about this? We're going to do the same calculation again, but with Bayes' theorem and using some of the math we did earlier. So you're going to see the sigmoid, you're going to see the log likelihoods, and then we're going to see what's happening. And by the way, so the reason this is related to naive Bayes is because we said the first and the second flip are independent, right? The way the first flip comes out does not affect the second flip. So every single thing in the second row, in the second flip, is independent of what happened in the first flip. This is why this is a naive Bayes problem. The first flip and the second flip do not affect each other as soon as you know the type, right? So the type of the coin affects both the first and the second flip. But given the type of the coin, the first and the second flip don't affect each other. So that's what makes this a naive Bayes problem. So let's see what happens if we just look at Bayes' theorem. So same problem again, we should get 1/5 as the answer. Let's do it with Bayes' theorem. So Bayes' theorem says the probability, okay, let me do what we had before. So before, and this was with, what is the probability of type heads, tails, given x1 is just heads, just given one thing. We came up with this calculation, and this was Bayes' theorem. So it's the probability that x1 equals heads, given y equals type heads, tails, times the probability y is type heads, tails. And then it was divided the probability that x1 equals heads, given y is type heads, tails, again, times the probability y is type heads, tails, plus the same thing from the other class. So the probability x1 equals heads, given type heads, heads, times the probability of type heads, heads. Okay, so it's sort of the relative ratio. Everything is flipped. When you flip it, you end up with this Bayes' theorem thing. So the probability of y given x is given in terms of the probability of x given y. And so last class, when we did this, this was 1/2 times 1/2 divided by 1/2 times 1/2 plus 1 times 1/2. So the key thing being that if it's the heads coin, that probability is 1. For the type heads coin, you always get a 1. Okay. So the way you can arrange this is by using the sigmoid function. This is something we saw. So in this particular case, all of these probabilities are a half. Because of the first choice was pulling the coin out of the bag, that is these halves over here, half, half, half. So you can arrange this probability by canceling out the half to get just something this. So if probability of each class is 1/2, then you can cancel that from the top and the bottom, and you just get this nice ratio. The probability of x1 equals heads, given type heads, tails, divided by the probability that x1 equals heads, given type heads, tails, plus the probability that x1 equals heads, given the other type heads, heads. Let's squeeze the heads in there. Okay, and we saw that if it's not a half, then you end up with a factor of log p over 1 minus p. But let's just, for simplicity, let's make this factor a half thing. And then what we did is we said, okay, you have a ratio like this. Anytime you have a ratio like this, you should think of the sigmoid function. And this is 1 over 1 plus e to the something. And what is the something? It is the log likelihood, the log of the probabilities. And instead of having a ratio inside the log, you have a difference. So it'll be the log of the probability of the evidence, x1 equals x, given heads, tails, minus the other one, minus the log of the other one. So let me highlight this one, the log of this one. And let me make more room. Let's draw this a little bit further over. Okay, so this is equal to 1 over 1 plus e to the difference of the logs. x1 is heads, given heads, tails, minus x1 is heads, given heads, heads. All right. So it's the ratio. It's a sigmoid. This is 1 minus sigmoid. And then you have these things. These are the log likelihoods of the either things. So when someone tells you some information, you can calculate the log likelihood for both classes. You just subtract the log likelihoods, and then you do the sigmoid. What is that in this case? So for this particular thing, it would be 1 plus e to the power. x1 is heads given type heads, tails. That is the log of a half. And then on the other side, you have log of 1 minus log of 1. Right? So it really is like, what is the probability of the thing you saw in either situation? Take the logs, subtract them, and apply the sigmoid function. So if you think about it like this, like it's very simple what's going on. Okay. And I think I maybe made a mistake. Maybe it should be the other way around. I think it should be minus plus. Yeah, it should be minus plus. Definitely should be minus plus. Okay. Minus this plus that. Because the log of 1 is 0. So this is saying like how unlikely is the thing that we saw to happen if you have the heads coin. And if we have the heads coin, the thing that we saw, seeing a heads, just has, it doesn't give you any information. Of course it happens 100% of the time. The log of 100% is 0. So the log likelihood has no help. So this is equal, or it was equal in this problem, to 1 over 1 plus e to the minus log of a half. Minus the log of a half is the same as the log of 2. E to the log of 2 is 2. So this is a 2, and the 2 really came from e to the log of 2, right? Okay, so that was how we got a third last time. Let's go through the calculation and just update it and add in 2 coins and see how things change, okay? Because things are going to change in a really nice way. If you have this point of view that what we are doing is adding together the log likelihoods. For 1 coin, you add together the likelihoods of the 1 coin. What happens if you have 2 independent coins adding? Let's see. So let's go back all the way to the beginning, and we're going to change the problem. We're going to do the after problem. Okay. So we're going to do the new problem. The new problem. And the new problem says we don't just have one heads, x1, we have 2 x's. We have x1 is heads, and x2 is also heads. So everywhere we're going to add in x2 is heads. That's going to be added in everywhere. And we're going to see how things change. x2 is heads. But everything else is the same, right? So it's still the same Bayesian calculation. We added in, now you have 2 coins coming up heads. So how does that change the probabilities? Well, the probabilities of the classes in green are still a half. But these probabilities change. So this probability over here, this probability changes. Instead of being a half, what is it? instead of being a half, it is 1/2 squared, right? It was a half for one single coin, and if you have 2 coins, it's a half squared, a half times a half. So it really is a half squared. Now it is a half squared. And this is the point, is that the probabilities multiply. Probabilities multiply for x1 and x2. Okay. Everything else stays the same. So this calculation over here, simplifying out the halves, that's the same. Let me add in x2 equals heads and x2 equals heads to this little thing. x2 has to be heads. And when we get to the next line, we can still apply the sigmoid, but now instead of x1 equals heads on its own, we have x1 equals heads and x2 equals heads. And what is the likelihood? And here is the cool thing. Oh, I forgot to write the word probability. The log probability. The log of the probability. So here's the nice thing. If the probabilities multiply, what do the logs of the probabilities do? Right? So if you think in terms of probabilities, we squared it. We multiplied the probabilities. If you think in terms of the logs of the probability, it's so nice because they simply add together. Right? So you really could just add on. You could say, okay, this whole calculation we did, this was the x1 calculation. And then there's a whole other thing that's going to be exactly the same. And it's going to be ln minus a half plus ln of 1. This is the x2 calculation. So the first thing is the log likelihood for x1. So the first coin flip, you get some information, has some likelihood from the heads coin, some likelihood from the heads tails coin. You take the log likelihoods, you add them together. That number is telling you, is it more likely to have come from heads or more likely to have come from the which coin, right? And then you do that log likelihood, that goes into the sigmoid and gives you the probability. This is such a beautiful thing because the x2 coin is saying do the same calculation exactly the same way for the x2 coin, take your 2 numbers, add them together, right? So each individual calculation is saying, okay, am I going more this way or more that way, right? x1 is saying more this way, more that way. x2 is saying more this way, more that way. You add the numbers together, that tells you the total amount. Is it more likely to be heads, tails, or tails, heads? So look, this is the same calculation. In our case, what is this going to be? Okay, we're going to have, before it was 2, what is it now? Let's do it a little bit slower. It's e minus log of a half plus 1. So before it was log of 2. Now it's going to be log of 2 plus log of 2. Also known as 1 over 1 plus e to the 2 log 2, right? And it really came from, one of the log 2s is from the first coin, one of the log 2s is from the second coin, and their evidence is just adding together inside this function. You add the evidence together, one of them gives a 2, the other one gives a 2. What is the total evidence? It is a 4. 1 over 1 plus 4, which is 1/5. The same answer we got before, but now we've broken it down by looking at the log likelihood, and the thing to realize is the log likelihoods add. So in naive Bayes, as long as things are independent, this is the beauty of naive Bayes, the log likelihoods add. Likelihoods add together. Okay, so whatever you got for the one coin, you just add it to whatever you got for the other coin. You add them all together, that tells you what to do. So it's all hidden inside the sigmoid function, which is maybe why it's hard to see, but inside the sigmoid function, everything is just adding in naive Bayes. This is why it's such a simple method that people like. All right, that was a lot of math and calculations to do a simple 1/5, but hopefully something was clear there. Any questions or comments about any of these calculations? Okay, let's see how to do it in a real life data set. The real life data set is our favorite toy classification real life data set, which is the Titanic data set. The Titanic data set. So here's the Titanic data set. Let me close this. So again, this is what the Titanic data set looks like. We have these passengers, and we have survived 0 or 1. Did they, when the Titanic sunk, did they die on the Titanic, or did they get rescued in a lifeboat? So here is their name, their age, their ticket, their fare. This is how much money they paid. This is the cabin they were in. Some of them didn't have cabins, I guess. This is what city they got on. I calculated something called log fare, which is the log of how much money they paid. And this is what class they were in. So P class tells you were they first class, second class, or third class. And siblings is, did they have siblings or parents on the boat? Because apparently that matters. I guess if you were with your parents, you were more likely to survive than if you were just alone on the boat. Okay, so that's the data set. And I added in, if they're male or female, I added in the age and the fare, the log fare. The first thing I did is I did simple linear logistic regression. I guess it's logistic regression, not linear regression. But I just did inside the sigmoid function, we did logistic regression just using these variables. Very simple. You run the scikit-learn logistic regression function. It does all that stuff we talked about a few weeks ago. Very similar to running linear regression like you did for your project, except for it's logistic regression. And at the end of the day, you get a model, and you can calculate the cross entropy loss for that model. You can calculate the accuracy. You can calculate the predictions. And the other thing you can do is you can make this nice curve. Am I in the right thing? Simple logistic model. Oh, this is telling me all the coefficients. So let me, before I look at the coefficients, you can calculate this curve that we talked about last class, the ROC curve. And so by varying the threshold, you can get, at this corner, we're saying, I predict every single person died. And at that corner, I predict every single person lived. And of course, those both have very bad error rates, but in two different ways. And by varying the threshold of the probability, you can get all these different things in between. So this is for the logistic model I came up with. This is the curve you get. And so you can see if you want the false positive rate to be 40%, then your true positive rate will be like 85% or something here. So by varying the probability in that model, you can get all sorts of different things. These are the coefficients it came up with, by the way. So it's saying what the model is doing is it multiplies the coefficient by the value of the thing, and then it adds them all together and takes the logistic function, right? So this is like, if you're a male, you get a score of minus 1.337 added to your number. If you're a female, you get a score of plus 1.262 added to your number. And then we add up all the numbers, and we apply the sigmoid to that. That's what we say your probability of surviving is. So you can see that being a female helps you quite a lot to survive. Being a male kind of makes it more likely you died, okay? And same thing, if you're in first class, then you get a big number added on. You get 1.2 added to your score. If you're in third class, you get negative 1.2 added to your score, right? So you can see how it works. It's just adding together a bunch of numbers, and then at the end it does the sigmoid of that. Okay. So that is logistic regression, what we did lots of classes ago, and this is the ROC curve for that. Any questions about the model or how the logistic regression works or anything like that? Okay, so very nice logistic regression. Oh, and here I made a little confusion matrix where I said classify at 50%, and this tells you the number of false positives and the number of false negatives exactly. So this is called the confusion matrix, which is sort of like one snapshot of this curve at a certain probability. Okay, the naive Bayes model, that's what we've been talking about today. And like I just showed you, what you do in the naive Bayes model is you calculate the log likelihood for survived, you calculate the log likelihood for died, and then for every single person, you just say, okay, what is the log likelihood for this one? What is the log likelihood for that one? You add them all together, and that gives you the number. So that before we were doing a number by doing these linear coefficients, and now we're also getting a number, and the way we get a number is we add together the scores for the log likelihood of each component. So let's see what that looks like. Okay, so here's the naive Bayes model. And the nice thing about this is you can handle two types of things together. So first I'm going to handle all the Gaussian-like variables. So there are two Gaussian-like variables. There is the age and the log fare. So I said these are continuous numbers. How much money you paid for your ticket could be any number. How old you are could be any number. And so I calculated their mean and standard deviation, and I treated them as a Gaussian bell curve. So for people who died, survived equals 0, they were 30 years old on average, and the standard deviation was 14 years. And for people who survived, their age was 28 years on average, and the standard deviation was 14.9. So by knowing the mean, you can sort of imagine, in fact, you don't have to imagine, let's do it in Desmos. Let's do it in Desmos, right? Actually, why don't we open the Desmos from the other day? Because you have to log in first. Okay. Okay, fine. I'll just make a new one. So I guess we have these two curves, e to the minus. One was 30 years old, right? The average is 30 years. I'll make the y-axis go from 0 to 2. Okay, I have to look around 30. Okay, there's the bell curve. So these are people who are 30 years old on average. And the other one, what they were 28 or something. One is x minus 28 years old. So we sort of have these two bell curves for survived and not survived. And if you give me some number, right, if you say I'm a person who's 35 years old, then you're more likely to be from the red one, right? That's exactly what we're doing. We're doing the likelihood for each one, and then we're going to do the logs and subtract them. So those are the two curves that we're thinking of in our thing. Very cartoonishly drawn. Okay. Where did the thing go? Not this one. This one. Okay. So that is for the age. And then I did the same thing for the log fare. And so this is the log of the amount of money you paid for your ticket, which has a mean of 2.7 if you died, and has a mean of 3.3 if you survived. So again, if you paid more money for your ticket, it was more likely you came from this survived class. All right, so these are Gaussians. They're really bell curves like we did before. The next categories are all things that are like coin flips. They are different classes. And so when I calculate the parameters, I'm calculating the probability that the coin flip is heads or tails. So you can think of this as like we have a bunch of types of coins, and I want to know what's the probability of heads and tails. So these are the Bernoulli-like variables, the coin flip-like variables. So things like male, female, what class you were in, and so on. And so here are all the different variables. So survived equals 0. These are all people who died. Of people who died, 67% of them were in third class, and 15% of them were in first class, right? So this tells you the different probabilities for these three classes. I treat it like a coin flip, every single thing. Which class were you in? I treat it like a coin flip, and I say, okay, the probability of coming up P class equals 3 is 0.678, and so on. And I do this for every single possible thing. Male or female, 85% of the people who died were male, 15% of the people who died were female. So this is a big coin flip that says, you know, you're more likely to be male than female if you died. And vice versa, over here, male and female if you survived. So I calculate all these parameters. I have the means and the variances for the Gaussians. I assume they're completely independent. I don't worry about the correlation. I have the means of all these things. I don't worry about the correlation, right? There would be a lot of correlations to deal with here, right? What's the probability you are male and you were in third class, right? There's a huge number, some huge number of ways these can interact, but I don't worry about that. I just calculate the probability for each of them. And then, very simple, this entire code, this line here is doing the sum, right? One line of code is just doing exactly what we did a second ago on pen and paper. We're computing the log likelihood for each class, and then we add them all together, right? So we're doing this calculation, like we saw over here. We calculate the log likelihood for each variable, and then at the end we just sum them all together, and that gives us the overall log likelihood. So this is all done by hand. Okay, so go through all the classes, calculate the negative log likelihood for each thing, right? And this is using the formula for the Gaussian variables. It's using the formula 1/2 difference of means squared, right? 1/2 times the difference of means squared divided by the standard deviation. That's the Gaussian likelihood formula. For the Bernoullis, it's using the cross entropy laws, right? The p times log p, right? Okay. And we add up these negative log likelihoods, NLL is negative log likelihood. We add them all up. There's two classes. We do it, what was the likelihood for dying? What was the likelihood for living? We do the difference, and that gives us some number, the log likelihood of dying minus living, 0, class 0 minus class 1. And then we apply the sigmoid function. And that gives us the probability, the naive Bayes probability of you living or dying. Okay, and using that, you can that's the model. There you go. Now you have the probability for each guy. We just assign them based on applying the sigmoid to the difference of the log likelihoods. That's exactly what we did over here. The sigmoid gets applied to the difference of the log likelihoods. Okay, and then you get, same kind of thing. You get a nice ROC curve. So just like before, for any given false positive rate, by changing the prior probability, changing the threshold, you can find the best possible true positive rate, and you get this nice curve. And it looks very similar to what we did in logistic regression, even though we made this silly assumption that things were independent. Which one of these is better? Is this one better? Or is that one better? Which model is doing that? Which one?
Logistic is better.
Why is logistic better?
Because it is doing this weighted average thing,
Mhm.
so it actually takes into consideration for each and every parameter. So
Right, so the thing is, sometimes one will be better, sometimes the other will be better.
Yeah.
It's not clear the answer to which one is better. You have to just investigate and look. And in this situation, there is one little number on the graph that is one possible way you can compare these things, right? One possible way is this AUC. Can I zoom in so the AUC gets bigger? This is the AUC. AUC stands for area under curve. And that is, you look at the ROC curve, and you just calculate the area underneath, and this is some kind of like average over all the possible true positive rates, how well it's doing. So this one had an AUC, the naive Bayes had an AUC of 83.83. 100, if it was 1.0, that would be perfect, right? That would be going all the way up to no error and then moving over like that. If it has 0.5, that is guessing, random guessing, right? So random guessing gets an AUC of 0.5. This model got an AUC of 0.83. Okay, and what about the linear logistic regression? That had an AUC of 0.86. So just very slightly better in terms of AUC. The curves are actually quite a bit different. If you look at the curve, I really should have plotted them on top of each other, but I didn't. If you look at the curves, they actually look quite a bit different. So this one's very vertical and then very flat, whereas the other one is more curvy, right? So what that means is if there's a particular value you care about, like maybe you care about a false positive rate of 0.2, right? You only want the townspeople to come and rescue you from a false positive of saying wolf, 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 1 out of 5 times you yell wolf. You only want it to be 1 out of 5 fake. So then maybe one model is better than the other, even though the other one is better on average. So the question of which is better is quite complicated. It depends what you care about. Okay, so finally, you can compare. You can compare the naive Bayes probability, the NB probability, to the LR probability, and you can sort of investigate which points are they classifying differently. Like they both care about different things. Which one is classifying better or worse? And you can see actually, like both of these models, they have a big class that has close to 0 probability, a big chunk that have close to 1 probability, and then there's a thing in between that the models aren't sure about. They're like, this person, I don't know, like 50%, maybe they lived or died, right? So they both have this peak in the middle, and the blue one, the naive Bayes probability has a bigger spike here in the middle than this one, the log probability, even though they both have a spike. So you can do all sorts of analysis. And this is essentially what you'll be doing for your project number 2. So you'll have that cooperators insurance data set. And I'm going to ask you to do the model 2 ways and compare them and make these ROC curves. One way, some kind of Bayesian way. It could be the naive Bayes. You could do a linear discriminant analysis. You could do a quadratic discriminant analysis. It's up to you. One way using logistic regression, which will be very similar to what you did in project 1, but logistic instead of linear. And then compare and contrast them and tell me about the differences. So more details will come out about that later this week. Any questions or comments? Okay, let's stop there for today. And so next class, it says there's no new videos, but make sure you watch those bootstrap videos. We're basically done classification now, and we're starting kind of like miscellaneous topics, starting with the bootstrap. So these are like fancy things you can do on top of regression or classification. Okay, so we'll stop there. See you guys on Thursday.